Mm.
Bro, you're supposed to ask to consent.
Oh, too bad. Okay. Transformers. All right. So, um, yeah, I mean, Transformers are like one of the most revolutionary architectures for NLP ever. It's widely used in academia and industry, and they achieved the state of the art for many tasks. Tasks like question answering. Oh, hello, Shimi. Tasks like question answering, uh, filling in like blanks in sentences, um, some creating generating text, summarizing articles, all of that right now is done with transformers. And there's a little uh, toy someone made with GPT-3, which is a transformer that auto completes text, and you can give it a prompt such as like I just said teach in here, and it sort of completed this little story. Pretty cool, yeah. So let's get we'll see how they work. And I guess last week, you already saw the attention mechanism, which is pretty much most of like the biggest building block in the transformer. But and it's the self attention. It's the dot product similarity self attention that we saw in last week. And today I'll go through like the attention mechanism a- in a bit more detail, and go over exactly how the transformer works. It shouldn't take too long of a workshop. Really, I'll just be covering like how it's trained and what exactly like it does at every step. Yeah. So also for context, I guess in the past we've gone over recurrent neural networks, uh, and the transformer is another sequence to sequence like method. Pretty much, you're just taking like say a sequence of words, like a sentence, which is a sequence of words in English, and translating them to French. And both like RNNs and transformers have an encoder and decoder. The encoder like captures some representation of a text, and the decoder translates it, or and the decoder like outputs the task output, which say could be like translating the text. And the biggest problem in all of these like and the LSTM is another type of RNN, and so is the GRU. And the biggest problem with these is that they struggle to retain information over long sequences. So if you can imagine, like if you're writing a story, there might be some like information 2 sentences ago that'll be important, like narrative points. But since like the recurrent neural network has a pretty small like uh, it's called like a hidden state, or like the LSTM has cell state and hidden states that it stores between every character. Turns out like it's pretty hard for it to actually remember what happened like two sentences ago, even though it does have like this cell state, which is supposed to act as the like long term memory in the LSTM. It still ends up forgetting what happened. It still ends up forgetting what happened a long time ago, and also it cannot directly access previous terms in the sequence, which means like it doesn't see like what it output, like what word it predicted like 2 words ago. um yeah, can't like directly, although it can like try to memorize it. As I already said, like that the cell state in the LSTM is pretty, it usually doesn't do that good of a job. And so transformer pretty much aims to fix that problem. And it's built out of like these are sort of the building blocks on the left, and on the right is the actual model. So scale dot product attention we sort of went over last week, but I'll go over it again. Then you can sort of you can add like some linear layers and uh copy it over a couple of times to make it fatter, and that's called multi-head attention. Pretty much it's multi because you have a bunch of attention heads instead of just one, and all of them are like performing some kind of computation. And what's actually pretty cool is you can see like where the attention heads point. So like in a sentence, you can see that when you're generating the word like not, you're looking at like the, I don't know, maybe like 2 words back. There is some like word. I'm not good at English, but when you're generating a word, these attention heads will point to different parts of a sentence to provide context on what word you should output. And so the transformer on the right, this is the full architecture. Although like you see the n times means like those blocks are copied over n times to make it like pretty deep. All it is the left part is an encoder, which you feed the inputs in. So like maybe a sentence in English. And then those sentences are sort of I go through this attention layer and a feed forward layer n times. And then it generates some kind of context that you feed into the decoder. And the decoder takes an output and it goes through like two additional attention layers. And then at the very end generates an output. And so the output embedding that you're feeding in to the decoder is the previous output. So if you wanted to output a sequence, you feed in like the previous word in the sentence, and it generates the next next word in the sentence for you. And then you can keep doing this until you reach like an end character, at which point like you'll stop generating your sequence. It's the same idea as an RNN.
Alexi, wait. So basically, the left part goes through everything that's come before, gives you context, and then the
Yeah.
right part, at the bottom, you take the output embedding, which is basically just the previous word, right?
Yeah.
So the left is giving you the entire context, and the right is just giving you the right bottom is just giving you the previous word.
Yeah, exactly.
Okay, cool.
Yeah. So it would be like English to French on the left would process the entire English sentence, right? And then the right part would be like if you're translating like I am, and say like the first word you predicted is like je, then you feed in je into the output embedding, and hopefully you get like whatever the French word for am is.
I J I am.
Yeah, yeah. Okay, wait.
Wait, that's
Uh,
I have.
oh.
Really?
I
Huh.
am is just sweet.
Just oh yeah.
Yes, yes.
Yeah, good point.
Yeah, so it would see that like the last word it predicted was je, and then be able to yeah, predict sweet. Um and like one thing to note is that the output embedding, it sorry, I was actually wrong. It doesn't I was it doesn't take in the last word, it takes in like the last the entire sequence that has been predicted so far. But yeah, sorry, I messed up. So what actually happens is like
I get it. I get it. I get
the amount of
it.
words it predicted so far, right? It
Right.
sees that, and then the rest is sort of like blanked out. But it goes like the entire sequence goes in, and then it predicts the next word.
So like in this case, it would be je.
Yeah, and so if you have like 3 words, like if you've done 3 words so far, and you want a fourth one, it you're feeding in like je suis yes, you're feeding in like the 3 previous words, and like you're getting the next fourth. So actually it's not like exactly token to token by token. It's like you're feeding in the like a whole sentence of a whole block, and you're getting the next word.
Wait, so just for clarity, so the left block takes
Mhm.
the initial inputs context up to that word, and
Yes.
then the right block takes the initial output context up to that word.
Um
What it's predicted so far, basically.
yeah, yeah.
Okay.
Yeah, the left one like takes in the entire English sentence. Is that yeah. Okay. So pretty much this is same as Joey's slide. For the actual attention mechanism, in this case, you're using scale dot product attention, and you're going to have like you're going to use a sort of dot product similarity between a key and a query, and you're going to get like, and all of those will be associated with values. So you'll have keys, values, and queries as matrices, and then you're going to take the row dot product between the keys and the queries to see like how similar your to see like which keys does your query want, and then you'll get the values associated with them. Yeah, so in this case, the sort of keys, or sorry, the values will be the actual sentence, and yeah, queries will end up being like representations of verbs or nouns that you're going to want, and yeah, so will keys. Yeah, so this is once again the math. You'll have in that like attention head, you have a 3 inputs: the query matrix, the key matrix, and the value matrix, and you're doing this matrix multiplication, scaling, softmax, which pretty much contribute like generates actual probabilities, generates like a sum, generates a distribution that sums to 1 for every row, and then you're multiplying it by your values. So all this does is sort of, it picks the parts of value, it picks the like rows and values which correspond like for which the query corresponds most closely to the keys. And yeah, we'll go step by step like in a bit. Yeah. So this is the like scaled dot product attention part, and I sort of just break it down step by step into like a little comic. You can read left to right, and then top to bottom. So the first thing it actually does is it takes like once you encode all of the sentences, so you get once you encode the entire sentence that you're feeding in, you have this sort of you have this matrix. You apply a linear transformation to get the queries, keys, and values. Then multiplying the queries and keys by each other gives you the scores, and the scores is going to, the size of that matrix is going to be like the length of the sentence by the length of the sentence. So it's sort of like on the bottom left, you can see it's like how much attention we want to give for each word, depending on each other, like for each word against all other words in the sentence. And you can like the for every row in that matrix, we generally want it to just add up to 1, since we're going to use it as a sort of mask. So what we do is we scale it, and then take the softmax, which is going to give us like that distribution that we want, where each row adds up to 1, and this matrix represents how like how much attention we for each word, how much attention we want to give to the other words. And then once you multiply that by the values, I think the dimension in this like graphic is a bit wrong, because you can't actually multiply those matrices, but it should be like 4. The amount of rows should be 4, and so when you actually multiply them out, you're gonna scale like if you see like, all right, here let me like give you concretely the dimensions. So the rows of the value matrix is gonna be the number of words, and the columns is gonna be the encoding size, and that's just like a hyperparameter you can choose. And so since like every row corresponds to a different value, corresponds to like every like one sort of column corresponds to some part of the encoding for every word, you're multiplying it in by those weights, and so you're pretty much end up scaling the value matrix to have like to under this like attention to attune it. Does that, I guess, make sense? Any questions there? Okay. And so we can stack them uh onto each other to be able to generate like to be able to have like different heads that attune for different parts of the text. And so it pretty much yeah, it they stack pretty similar to how like convolutional filters stack uh they stack in like different channels. As you saw, like from convolutional, there's like height, width, and the number of channels, and it's very similar in this way. And it's very similar like in this case where you just sort of have like some h number of channels, and every channel has its own like has a different linear layer and has a different like dot product attention weights. And yeah, and then after you have like after you do all of these channels, you concatenate them and feed it into another linear layer. Um, and that's the output of the multi-head attention. So yeah, like I was saying, you apply a linear transformation to the values, keys, and queries before feeding into the dot product attention, which is this linear. And so now you define this multi-head attention block as the like you split it up into different attention heads. If you can see my cursor, like each attention head is the dot product attention that we saw before. Yeah, and except now like there's another linear matrix multiplying it, and then when you compute all of these heads, you concatenate them back together, which is this block, and multiply it by a linear layer. And as you might imagine, the number of parameters is pretty large, and just to make it more concrete, all the like the queries, keys, and values are both like shaped L by D. Disregarding the bash size, they're like the shape is L by D, where L is the length of your sentence, and D is like a hyperparameter you choose, which is the depth of like the encoding size of the model. And yeah, there's like the weights you multiplied by can be like D model by another hyperparameter. And yeah, not exactly too important. I think you can go back to like to see the weights to see how the math works out, but it'll sort of it fits pretty nicely together. But yeah, I guess one thing you can definitely take away is like the number of parameters you have in these W matrices uh like starts increasing a lot when your sentence length increases, and that's not very good. In general, like transformers have probably the most like parameters out of any like deep learning model. Um, yeah, and here when you have h equals 2 or n equals, I think let's just say h equals 2, you have two self-attention like heads, and all of them compute this sort of, all of them compute that like self-attention output, and then you can stack them together and feed them into a linear layer.
Wait, I'm confused. Why do we have multiple attention heads? I don't get it because we're trying to find the attention for for the same words, right, in the sentence. So why are we
Yeah.
having different heads for that?
Yeah, and so when like for one word, you might want to look at different parts, right, of the sentence. You know, if you're saying like something like the word it, or I can't like I should have had more examples, but the motivation is that like for different words you might want to look at different parts of a sentence. Like for one word, you might want to look at like the name previously used, the verb previously used, and like the adverb previously used. And so that's where you need like you need like many attention heads so that you can point at those different parts. Does that make sense?
Yeah, but then I'm wondering if each of these outputs like an attention matrix where each score gives you how much attention you want to pay to each word.
Yeah.
What confuses me is Would that mean that one head will pay more attention to one word than the others?
Yeah, so like you see this like softmax output, right? Um, yeah, exactly. Like one word pays more attention to like a different word in the sentence. And in practice, like when you have different multiple attention heads, like here the word how, and one head might point to how, and another head might like point to R.
Hmm.
It's not gonna be like it's not gonna be like 0.5, 0.5, right?
Hmm.
It's gonna be like 0.9, and in another head like 0.9 here.
Hmm.
So it like each head uh like in the end ends up like pointing to a very specific other word.
Mhm.
And
Okay.
then when you concatenate, you're like combining that context from
Wait,
all the heads.
we concatenate or we add?
Uh concatenate like so the output to each head is this is like the Q and K compute this softmax like mask, right? They compute like the intention mask,
Mhm.
and then you multiply it by values, and then like you as you can see like the output for each of these scaled dot product attentions you concatenate.
Yeah,
So
but
this attention weights by values, right?
Hmm.
It selects like one word, and then or yeah, like for every word it selects like pretty much one word, and then you concatenate like all the different attention heads to see like what words you want to look at before.
Okay. Okay, cool. That makes
Yeah,
sense.
yeah. The paper actually like it's the paper is surprisingly leaves a lot of like details out. It's very short and kind of like I mean it's interesting to read, but I feel like it's hard to like gain like super intuitive understanding. So and like I'm not like extremely familiar with this area. I was just that's like sort of what I got from the paper and like a couple other resources. Yeah, so now like finally the full transformer. Um apart from having this multi-head, like you can see the little module multi-head attention, which is like exactly this, just packed abstracted away into a little box. And the full transformer, like I already said, it takes in the full sentence input, uh, and it applies multi-head attention, and then it also adds it in like adds the value in without attention. So it's the same like in ResNet. The what you saw is like these what you saw skip connections where every other layer is skipped to make like the model learn better because the gradient propagates better. And this is like exactly the same here you have like the exact same thing where it's pretty much a skip connection where if this multi-head attention like part is not very useful, you just skip it. And then you also have like a regular like feed forward network. So just to allow it to have like a deeper representation, because as you saw, like these the like scale dot product attention itself, it doesn't actually like it doesn't compute any like deep information. All it does is multiply the value by a mask, right? So and the multi-head attention, it only has like these two linear layers, and this linear layer, it since it's computing the like it's mostly computing the queries and the keys, and also like changes the value up a bit. But like this multi-head attention does not add much depth to the network. So we also have a feed forward like module you put after the attention, and then again it has this like skip connection, and then you copy paste the encoder over like up above n times, and take the representation it gives you to feed into the decoder. And so now the decoder actually has like two attention blocks. You can see like little orange boxes. Whenever it's fed in, like this, whenever it's fed in the output, it you can see like it says masked multi-head attention, and that's what I was saying about like the transformer only sees the words it outputs so far. Like there's no word, you can't obviously you can't see like what words you're going to output in the future, So that's why it's like masked. Because in practice, like those values in the like softmax attention mask, you have those values become like 0. Like you're never looking ahead as you're decoding. And then you have another like multi-head attention where you're actually taking the input from your decoder. And you'll see what that means. And then you have like these feed forward layer, and you copy paste that n times, and in the end generate like a softmax output to select the next word. And yeah, so you can see there's a skip connection, layer norm, linear value, linear layer norm. Not sure what the top right or where the top right one is. I kind of lost. It is somewhere in here. I just forgot where it is. It might be the like feed forward skip connection that I was talking. Yeah, it's the feed forward skip connection that I was talking about, where there's like a linear and a value, and then again a linear, and you can like skip all of that. And so the way that you can see, like this is the decoder outputs like token by token, and it's going to when you first feed it in, it's just you just feed in like a start token, which means like that you're starting the sentence, and the decoder, and all of these are masked, and then the decoder outputs like I, and you feed in start I, and decoder outputs am, start I am, decoder outputs fine, start I am fine, and decoder ends the sentence. And like that's you just inputted you just went through like generating like one working on one sentence. And yeah, in this one maybe it's like a conversation, like you're asked, hi, how are you, and you say, I am fine. Yeah, so formalizing the like masking part, you after like in this multi-head attention, after you have those scaled scores from softmax, you apply this look ahead mask, which like you just added. And then when you take the softmax again, when you before taking the softmax, after dividing by square root d, you add the look ahead mask, and when you take softmax, the negative infinity values are going to be 0. So it's kind of like it doesn't make much sense to have these I am fine, since for like start it hasn't output I am fine yet, so those are like blanked out, and it doesn't look at what is going to output in the future because it can't. Okay, and so what happens, like the way the encoder works, the way the encoder helps the decoder is the encoder generates the keys and values for the second layer. So it's this. You can see little 2 lines are fed into this attention part. And so the decoder, like, the encoder tells you like the values you want to select from, like the values you want to apply attention onto, and the keys, and the decoder generates the actual query. The intuition for this, I think, is like, whoops. The intuition for this is the decoder is able to like, the decoder's responsibility is to know, like, is to generate the query. So it wants to know what like, it's looking for like these sort of keys. It's looking for like some sort of context, some feature representation, and the encoder provides the keys and values. So if this is like a conversation, the encoder provides like what has been said, and the decoder queries, like the decoder provides a specific query for what it wants to output, like the word it's looking for at this point. And yeah, I was actually like, I was taking some of the visuals from the video that I just screenshotted a lot of times, and they actually got this part wrong, I think. So it's honestly, it can be pretty blurry, but yeah. And in the paper, the way I like realized it's the encoder generates the keys and values is I just looked at the little graphic they made in the paper, and even though they didn't explicitly say it. So yeah, this can be quite like there's a lot of detail, I feel like, that the paper goes over. But yeah, the encoder generates the keys and values. And at the end, when you want to output the next word, you have like a linear layer where that generates a vector, or like a vector that's the size of your vocabulary, and then you apply softmax, and like in this case, you can see that it wants like the last word in the vocabulary. Sorry. And then yeah, like pretty much the encoder encodes some context and feeds it into like every decoder block while like it's computing the output. And so whoops, okay. And so yeah, that's pretty much the transformer. Do you guys have any questions? Okay, cool. So we'll go into GPT, which is like the OpenAI language model. Whoops. OpenAI language model, which is able to get like super high performance on pretty much all the tasks. Right now, the last one they made is like GPT-3, which is it's just gotten bigger, and I don't think the key like technique has changed, but yeah, they made like this GPT, to be clear, is just a transformer, but the advancement they made is like they figured out how to train it very well, such that like they're able to just learn a generic language and then apply it to different tasks. So yeah, you can say like they train on just a large amount of text like Wikipedia, and they don't really have like they don't have any sort of labels. So if they want to do well on like a task such as like answering a question, they don't just take like a bunch of questions and answers. They actually just they take like a huge amount of text that they just scraped from the internet, and they learn what is like they learn how to speak English on that like large amount of text, and then they're able to adjust the model such that it actually does the task, like question answering. And yeah, they like turns out that sort of doing it this way, they're able to set like the state of the art like benchmarks for like every single language task. So yeah, it turns out like all the language all the different language tasks like translating or question answering or generating paragraphs, like all of them like have something in common that they're able to like prove by doing this, because they're able to like just train on a large amount of like just a large amount of text, and then only then like fit to the specific task. And like the way they fit to the specific task, they use like much less computation than any other like paper. And so like and they still were able to beat like the papers that train specifically on that task. So it proves like, you know, language is pretty general, and if you're good at question answering, you might be good at writing stories. Okay, so let's get into like what I mean by training on a large amount of text. So it's called unsupervised pre-training, or GPT stands for something pre-training. I forgot the exact word. If you want to Google that. And the objective it trains on. Well, so like first we need to define the L1, like the loss is going to train on, and all it really trains on is the log probability, the log probability of the next word, given all the like previous words, and the parameters of the model. So pretty much like you can derive this. Say like you have like some sentence, right? And the probability of that sentence is like the probability of the first word multiplied by the probability of the second word given the first word, and then like probability of the third word given the first and second word. So like it's like this conditional probabilities that you're stacking. And so your model is going to output like the probability of the sentence occurring if you multiply like probability of first word by probability of first word, second word given first. When you multiply that out, that's like the probability of the sentence, which is like pretty abstract, but you know, like in general, like, you know, your language is like a distribution of all the sentences, and so we want to maximize like the probability of the sentences from our text corpus of text occurring. And you know what I described is like a product. If you take the log of that product, it can actually, you can break it down into sums, because like log of a times b plus times c is like log a plus log b plus log c. And so you're just like, you're maximizing the probability of your sentence occurring. And by taking the log, like if you maximize the log, you also maximize the original probability, because it's like strictly increasing. And you can break it down into a sum, and that way like you can, it's much easier to train. And yeah, so you're maximizing like you're maximizing the probability of every sentence in your text occurring. And they just used like a transformer where they pretty much fed in, they just feed in like this, they have a bunch of hidden layers between the transformers. Sorry, they literally just use a transformer architecture like this. This notation you see on the right with like H0, HL is just like applying another transformer block on top of each other. And then they just use like, they simply predict the next word in the text. And so, and then they just train to get really good at predicting the next word. And that like is seen as a sort of pre-training, just getting really good at like the English language. And then when they actually want to have like a question answer task, what they do is instead they maximize P of Y given the input. So they maximize like your probability of getting the output given the input, which is just supervised learning. And so they literally just do supervised learning on like a specific task after they like learn this English language. And what they found is they can actually do better. They can even do better by learning both the English language and the task at the same time, which is why they can combine the losses. They can combine like these objectives. They're not losses. You're maximizing them. So they're objectives into like this you know, L3 objective, which is both learning the English language and like your question answering task. Okay, do you guys have any questions?
You were talking about how we output like a sentence, right?
Mhm.
And for each sentence, we look at a word and we find its probability. All right, or rather, we take the word with the maximum probability and then we keep multiplying that for every word across the sentence, correct?
Yeah,
Then that's what we're trying to minimize.
maximize. We're trying to,
Maximize, sorry, my bad. Yeah, maximize.
yeah.
Yeah. All of these are probabilities, which means they're between 0 and 1, right?
Mhm.
So wouldn't this disincentivize GPT from making longer sentences? Because the more words you have, the higher the chances that you're gonna have end up with a smaller number.
Mm. Wow. Um, you're only predicting like the next word. You're not predicting like the whole sentence,
Oh.
and so that way it doesn't like,
Hmm.
it's yeah, it's never, I like, I know what you mean. I see what you mean. And like when you generate like text, if you generate like a paragraph of text, that might be the case where it's like, you know, a short sentence has a much higher probability. But like in training it, like that's not a problem.
Ah, cool. Thank you.
Yeah. Okay. And so onto the structure they actually used. So they only used decoders for they only used like the decoder part of the transformer. And yeah, it's pretty standard. Since there's no encoder, the decoder doesn't have decoder doesn't have the like part that takes in the encoder output. It's literally just self-attention and a feed-forward block and a feed-forward neural network. And yeah, they they just stacked a bunch of those, and at the end that outputs the probability. And so the big, like a really big part of the progress they made is actually like something called a task aware input transformation during fine tuning, which I'm not gonna go over and teach, but that's sort of how they were able to get like super good results on the different tasks after like learning the general English language. They are able to like really like they're able to adapt the model for all the different tasks really well. And they trained this on like millions of web pages, and they like the original paper beat the state of the art on question answering, machine translation, reading comprehension, and summarization, and sentiment analysis too, I think. And so there's also like models like GPT-2 and 3. 3 is like pretty new. It's within a year that do even better. So, and all they did is they just tuned up the number of those decoders, transformer decoders, and the sentence size. So, you know, they actually use like, in this case, they use 4,000. Like the max sentence can be like length 4,000. So yeah, that's pretty long. That's like a 4,000 word essay. That's long. Yeah, and it does better. Okay, that's the whole presentation. Do you have any questions on GPT or anything so far?
Wait, so are there like any limitations to GPT? Because like if it's like this where the pre-trained model actually understands English, then isn't it sort of approaching general intelligence where it can answer anything as long as it has the data for it?
So I don't think like no one, I don't think people have figured out how to give it the data when answering questions. If that makes sense. Like although I'm not too sure about this, but I know like most of the applications, it just you know, you're not like it has a pretty limited like knowledge of facts. It may, I don't know, like I'm not sure if it knows how to like add numbers. Like if you tell it like 5 + 5 equals and then tell it to complete the next sentence, complete the next letter, like I don't know if it would say 10. But yeah, I mean, I see what you mean. Although like in the end it is just a language model. Like it's just predicting the next word given like some sentence. But you could possibly like say that if you know language, you're if you, I don't know. I'll let, like I'm pretty sure it can't add. If you like, pretty sure you can't tell it like some like random number plus another random number equals, and then like expect it to give you the answer. So if it can't add, it's probably not intelligent.
That's true. Yeah, cool.
Yeah. So, but yeah, I mean, this is pretty interesting. Also, I mean, it only really can only know the facts it trained on. So, you know, it's not very adaptive, or like, you know, can't learn new things. Or I guess it can, but it can't like take in some fact when, you know, training. Can't like, yeah, I don't know. Hopefully that
But I
helps.
don't think that's how you define general intelligence, wherein it can just answer any question that you ask it to. I feel like general intelligence would be properly general. Like, for example, if I ask it to like start up a Minecraft server and play with me, it's not gonna do that, right? It's definitely not general. It can only just do exactly what you ask it to.
Mm, I see. So if it was intelligent, it wouldn't play Minecraft with you. That's
Yeah.
tough.
No, I'm saying if it was
Okay.
intelligent, it would play Minecraft.
Oh, yeah, I don't know. I don't know. It's interesting debate. I don't think not exactly like familiar. I don't know if the best way to answer these questions, so I'll just nod. Okay, I'll stop the recording now.